Good evening, my name is Sing Chun Lin and I did my project on maximum power point trackers or MPPT for photovoltaics. So what is a maximum power point tracker? It outputs maximum power to the load given varying temperature and radiance of the sun. If you look at the IV curve of the solar cell, you can see a maximum power point marked. The goal is to stay there given varying conditions. The hill climbing method, which I'll be using the maximum power point tracker that I created, is interested in the derivative power with respect to duty cycle. The duty cycle I'm talking about is the duty cycle of the DC to DC converter that will be used to step up or step down the voltage. The duty cycle changes the maximum power point because it changes the effective internal resistance of the solar cell. This is the maximum power point tracker I created in Simulink. The first aspect I'm going to talk about is the solar panel and its input and parameters, which is outlined in blue. The top graph represents illumination on the solar panel and the bottom graph represents the temperature of the solar cell. Next, we're going to where the bulk of the maximum power point tracking happens. In yellow, you'll see an MPPT block and the inputs into it are the voltage and current produced by the solar cell and sampled every 10 seconds, and the output of the MPPT block is the duty cycle of the DC to DC buck converter. The basic logic inside the maximum power point tracker is that it compares the current power output with the previous power output. Once you compare the power, you compare the voltage and change the duty cycle accordingly. There are two branches that result in an increase in the duty cycle. The other two branches, you decrement the duty cycle. If we only compare the power to determine whether or not to increase or decrease the duty cycle, we could do all the computations in the Z domain. The next section where you're looking into is the buck converter. The buck converter steps down the DC voltage. If the photovoltaic panel was powering a device that did not need as much power as the photovoltaic panel was outputting, then the appropriate amount of power would be outputted from the maximum power point tracker. Next, we'll look at the measurements at the output of the maximum power point tracker system. At the output, we are measuring the current voltage and multiplying to get the power. We're sampling the measurement of the current and voltage every microsecond. This is a graph of the power versus time curve at the output of the maximum power point tracker. You can see that the power follows a similar curve to the radiance curve. This is because power is impacted by the radiance of the sun. Now we compare this with the graph of power with no maximum power point tracking. The power changes according to the IV characteristic of the photovoltaic, so it doesn't stay at a maximum power point. Now, if you zoom in, you can see the exponential curve that's characteristic of a photovoltaic cell. Now we're sampling the voltage and current output every millisecond instead of every microsecond. The output looks totally different from before. And with no maximum power point tracking, you can see that this graph is almost the same as the graph of the power versus time with maximum power point tracking. This shows that with an infrequent sampling frequency, the maximum power point tracker doesn't do anything. These are my sources. Thanks for watching.